not cause consternation. To reveal, C to sender and receiver. Three, let W be uniform over the set 1, 2 through 2 to the NR. You say, "Well, that's sort of a use. You're specifying how often you use each code word." It'll give us what the behavior of the average of the lambda i's is, and from that we'll be able to determine a good code word by throwing away the worst half of the lambda i's. So this is simply an artifice to symmetrize the problem and to allow us to deal with a quantity which we can then prune and manipulate to give us the answer we want. In other words, it's not a specification of how you have to use the channel. 4, send the sequence associated with this randomly chosen W. 5, receiver observes Yn, and what's the distribution of Yn? It's drawn according to P of Yi given Xi of W from I equals 1 to N. In other words, the Y's are conditionally independent, drawn according to the conditional distributions of the input at the associated times. 6, use jointly typical decoding to assign W hat. Specifically, let W hat equals I if Xni and the received Yn are jointly typical. And no other such I so it must be uniquely typical. Otherwise, set W hat equals 0, which you'll note is not on the list of 1 through 2 to the NR. We're essentially declaring an error. All right, now we have the error analysis. So need this. here's how good this code is. Let EI, because most of the time it's going to be an error event, so E for error will be the event that XNI, that's code word, and YN are jointly typical. And we'll define this for I equals 1, 2, through 2 to the NR. Here's how we're going to, without loss of generality, let W equal 1. In other words, this random W, might as well let it be the first code word. I generated all the code words according to the same distribution and independently. And my decoding rule is symmetric. I just look for the uniquely jointly typical cause for my effect. So I will calculate the conditional probability of error given W equals 1. That will be the same as the overall probability of error averaged over all W, where W is uniformly drawn. So here it is. Here's my code book. X1, X2 to the NR. I'm going to run this through the channel. X1 through the channel P of Y given X, and I get Y. I better put ends on these, N, N, N. And these are sequences of length N. Okay? And from YN I get W hat. And the probability of error is the probability of error given that W equals 1. Why? Because the overall probability of error is the average of these, and these are all the same by the symmetry of the code construction. Okay, but what is this? This is the probability of E1 complement union E2 union union E2 to the NR. In other words, I make an error if W hat is not equal to 1. That is, if this event, Xn of 1, Yn, or typical, does not occur. That would be sad. I put X into a channel and I get an untypical output. Probability of that is arbitrarily small, but that's one of the possibilities for the error. Now, what about E2 or EI? Well, what's the probability that Xn of I and Yn are jointly typical? What's the probability of this event, EI? So, I make an error if I don't entertain 1 as the code word that was sent, or if I do entertain any other index I. All right, but the probability of A union B is less than P of A plus P of B. So this is P of E1 complement plus summation of P of EI from I equals 2 to 2 to the NR. All right? Now, this is less than or equal to epsilon by AEP theorem, if you wish, by item 1 in the statement of that theorem. And this is less than 2 to the minus n I minus 3 epsilon. Again, by the AEP theorem. The probability that some other randomly chosen code word with the right marginal, but is otherwise independent, looks as if it's jointly distributed with y according to the channel. This is that. And how many terms are there? Less than 2 to the NR. So, we got thus PE probability of error is less than epsilon plus 2 to the n r minus I minus 3 epsilon. Sort of. So it goes to 0, because I can make epsilon arbitrarily small, for r less than I of xy minus 3 epsilon. Great. So now we're done, because this probability of error is equal to summation of lambda I, the conditional probabilities of error, 1 to 2 to the NR, divided by 2 to the NR. This is what the probability of error is. But notice we averaging over codes too. So here's what we should do. We haven't quite finished it. We've said we can achieve any r less than I. Well, it would be crazy not to make I as large as possible. So, for next time, we'll set P of x equals P star of x and I of xy equals C. And now we can achieve any rate up to C. And then true for true on average for random code So therefore there exists, this means there exists, a code C star such that probability of error given C star, I'll put a C star here, less than, all right, goes to 0. All right, less than epsilon plus 2 to the minus n